Okay, for this video, we are going to take a look at isotopes. So, very first thing is, what is an isotope? So, an isotope are atoms of the same element with different mass numbers. Or I can think of it as atoms of the same element with a different number of neutrons. So let's talk about what mass number is here. So I say that they have different mass numbers, but what does that actually mean? So a mass number is the total mass of an atom, and this is made up of protons, which remember has one atomic mass unit, and neutrons, which also has one atomic mass unit. Now these are in the center of our atom. Remember, that's our nucleus. And we assume electrons have no mass. Now, is that 100% true? No. Electrons have some amount of mass, but not enough for us to worry about it. And now remember, AMU, that's our unit that's like grams, but we couldn't use grams because atoms are so tiny. We had to give them their own unit. So that's what that AMU is. Okay, so that's what we're talking about, mass number. The mass number can change based on our number of neutrons, but we cannot change our proton number because we're talking about the same element. And remember, for us to have the same element, it has to have the same number of protons. So let's talk about some examples here. The most common example that we hear is carbon dating. Okay, it's carbon-14 dating. So I can have our most abundant carbon is carbon-12. And that 12 is my mass number. And it's carbon, so it has 6 protons. We're going to talk about what this is in just a minute. Or I could have carbon-13. Most people haven't even heard about carbon-13, which makes up about 1% of carbon on Earth. Or we can have carbon-14, which is what we use for carbon dating. So these are all carbon because they have 6 protons, but they are isotopes because we have different mass numbers. So these at the top are the mass numbers. Okay. So let's talk about calculating this mass number. So mass number protons plus neutrons. So again, we're talking about the mass number was made up of protons and neutrons, so we're just adding those together. So let's take a look at an example. Let's say I have a magnesium atom with 13 neutrons. Has what mass number? So I know here that I need the information for my protons and my neutrons. So magnesium, Mg, It is element number 12. So I have 12 protons here. Plus, I just told you that I had 13 neutrons. So my mass number here is going to be 25 AMU. Now, most of the time when we're writing it like this, or most of the time we will write it like this, so we don't use that AMU, but occasionally you will see it. When we write it in this nuclear isotopic notation, which we're going to do in just a second, that number, we know that it is AMU because that's part of why we write it in this format. It's more user-friendly. Now, lots of times people say, well, the atomic mass is there at the bottom. If we look at our key, that's the average atomic mass. We are looking for mass number. Those are not the same thing. So mass number is in whole number increments because we're looking at the protons and the neutrons. Average atomic mass deals with abundancy, so how much we have of each one naturally occurring. So for me to figure out the average atomic mass of carbon, I'm going to have to look at all three of these, what percentage of each makes up my overall carbon on Earth, and then do some calculations. Those calculations we do with average atomic mass. That is not what we're doing here with isotopes. With isotopes, we're focusing on using this mass number equation. Mass number equals protons plus neutrons. Okay. Let's check out another example down here. Let's say that an atom has 12 protons and 11 neutrons. What is the mass number? Now, I'm still looking at 12 protons, so I could look at my periodic table and see that that is Mg, that is magnesium. But if all I'm asking you is the mass number, you actually don't need to know what element it is unless it's a problem like this one above where I don't give you the information on the proton. So instead, we would just say 12 plus 11 protons plus neutrons equals 23 AMU. So with ions, if you're writing an ion, you have to know what element it is because you're writing that element symbol and then our charge superscripted to the right. For mass number, if all you're looking for is mass number, you're just going to need that number and unit. When we get to notation, which is the next thing we're going to look at, that's when you're going to have to make sure that you have that element. So let's take a look at some ways for us to write isotopes. Now that we know our mass number, we know our proton number, and we know how to do charges. So the first thing that we can do is called a hyphen notation. So again, we're looking at how do we write isotopes. So our first option is our hyphen notation. And what this does is you have the element hyphen your mass number. You can use the whole name or element symbol. So an example of this may be something like uranium-235. So my options here would be to write uranium out hyphen 235, or I can write uranium-235. The only information you can get from a hyphen notation is the element, and because you know the element, you know your number of protons, and the mass number. So 235 is just the mass number. There's nowhere here for me to put anything about charges if it's an ion. Okay. So this is easier to use, say, if you're typing a paper or something like that, or when charge doesn't really matter. So sometimes in nuclear things you'll see mostly hyphen in the written papers, and then in their actual work you'll see it in this next type of notation. So this is not as beneficial for us to look at, but it is a quicker way for us to get some information. Let's check out the way that we are more likely to be writing these and what you'll see when we do nuclear. This is what we call the nuclear isotopic notation. And the way this is going to work is you're going to have your element symbol, your charge in your top right corner, just like we did with our ions, our mass number in our top left corner, and our proton number in our bottom left corner. Now remember, proton number is the same as atomic number. So those are the same thing down there. So if we were taking this same example of this right here, and we were going to make it into a nuclear isotopic notation, then it would look like, maybe, uranium, 235. And if I look at the periodic table, uranium has 92 protons. Now based on this, it has no charge, so I don't need to write a charge there. So I'm good to go with that. But let's say I do have something with a charge. Let's say I have a calcium. So I have calcium. It has 20 protons. Let's say it has a mass number of 44 and a +2 charge. So this one would be a neutral atom. This one would be an ion. That charge right there is what's telling me. This gives me a lot more quick information than the hyphen notation would. Okay. So those are going to be our two ways to write those. Now for this first one, you're pretty much going to be doing the same process as what we did with our mass numbers. So I'm not going to work any more examples on that, but if you have a question, please let me know. What I do want us to look at are some examples for this nuclear isotopic notation. Okay. So if I have an atom that has, let's say, 38 protons, 40 neutrons, and 36 electrons. And I want you to write the nuclear isotopic notation. So first thing I need to do is figure out what element this is. So I got 38 protons, so I need to go to my periodic table and figure out what element 38 is. So I look right there, it's strontium. So I now need to go ahead and write my element symbol, so capital S, lowercase r. I have 38 protons, so I can go ahead and write 38 right there. Now I need to figure out my mass number. So remember, mass number is protons plus neutrons. So I'm looking for my mass number. I have 38 protons, 40 neutrons. Okay. Add those together, 78. And then let's calculate our charge. Remember, charge is protons minus electrons. I'm looking for my charge. I have 38 protons minus 36 electrons. So that gives me 2. Remember, for charges, we always have to say if they're positive or negative. So that is strontium-78 with a +2 charge. So that is a cation of strontium-78. Now, if I were to write this in a hyphen notation, I could not include that charge. So this is a better option for me than looking just for that hyphen notation. Okay, let's do another example. let's say I have a nitrogen atom with 7 neutrons and 10 electrons. The E with the little minus means electrons. I abbreviate P for protons and N for neutrons. So let's check out this next example. So I have a nitrogen atom. So I know I can look at my periodic table and my element symbol is just going to be a capital N. Nitrogen atom also tells me, because nitrogen is our 7th element, that we have 7 protons. So I'm going to go ahead and write my 7 down here in my bottom left corner. Now we need to calculate our mass number. Mass number is protons plus neutrons. So I have 7 protons, 7 neutrons. It is totally fine that those are the same number. That's very possible. Okay, so don't let that throw you off, make you feel like you've done something wrong. So 7 and 7, that gives me 14. And then I need to check out my charge here. Remember, charge is protons minus electrons. So I have 7 protons minus 10 electrons. So X gives me -3. So I'm going to put my -3 up there. So that is the way to work through it if you are looking at information of your subatomic particles and you are writing a nuclear or an isotopic nuclear notation. But sometimes you'll be given the notation and I will ask you for that information. So let's take a look at that. So let's say I give you, move my periodic table here. Let's say I give you K. So I give you this information and I want you to tell me the mass number, the neutrons, protons, and electrons. Well, 2 things you can tell me straight from this, okay, and that's the mass number, so that's 39, and the proton number, which is 19. If I were to ask you for the charge, you would also know that from this, because it is a +1. Now, for the neutrons and electrons, we're going to have to work through those problems again. So when I'm looking for neutrons, I'm going to take that mass number equation that we've been working with. So remember, mass number equals protons plus neutrons. This time I have my mass number. My mass number is 39. I have 19 protons, and I need to know how many neutrons. So I'm going to subtract my 19 from both sides, and I have 20. So I have 20 neutrons. Now let's check out calculating our charge here. Remember that charge is protons minus electrons. So my charge is a +1. I have 19 protons and I'm figuring out my number of electrons. So I'm saying 19 minus what gets me a 1? That's 18. So I have 18 electrons. Let's look at one more example here. Let's say that I give you, let's do chlorine. That's the information I give you. I'm not promising these are real isotopes. I'm making them up, but will be good for practice. So let's say again we're going to look for our mass number, our number of neutrons, number of protons, our electrons, and our charge. Well, straight from this, we can get 3 pieces of information. My top left corner is my mass number, so I have 20 AMU there. Oops. I don't know why I wrote 20. That's very much not a real one. Let's try that again. Let's see. 37. Okay. 20 was not even close to being a real thing. Okay. So, top left corner. So, 37 is my mass number. This bottom left is my proton number. And I also know my charge. Now remember, if nothing's written up there, then it's neutral. If something is neutral, it has a charge of 0. So those are my 3 pieces of information I can get pretty quickly. Now let's solve for our neutrons and electrons. Remember, when I'm solving for my neutrons, I have to use that mass number equation. So mass number equals protons plus neutrons. So my mass number is 37. I have 17 protons. I don't know my neutrons. So 37 minus 17 gives me 20 neutrons. And then let's check out our electrons. We have to use that charge equation again. So charge equals protons minus electrons. Our charge is 0. I have 17 protons. I don't know my electrons. So I'm saying 17 minus what gets me 0, which is 17. So remember, if my charge is 0, my protons and electrons are equal. That's what makes something a neutral atom. So those are some examples, and we'll be working with some more. Please let me know if you have questions.